the Potpourri session plans and systems. We have one cancellation from Matthew Marshall, who was not able to make it today, which means we will expand the time available to accommodate the two remaining speakers, and they have been gracious to extend their talks with us today. The first speaker is Dr. Kumar Krishen from the NASA Johnson Space Center. He will be presenting a paper entitled, and this is a change from what's in the program, it's entitled, at this time, Advanced Technologies for NASA Space Programs. He has a limited number of copies available up here at the desk for release here. If the copies run out and you wish for him to send you a copy, you can either leave your name and address to the paper here or leave your business card, and he will send those to you. So, without any further ado, Dr. Krishen, please.
Let me mention this, that the presentation is a little bit more technically inclined. I will try to, I realize that the paper is already published, so you can read the technical details from the paper. So what I'll try to do is give you my philosophical attitude towards technology in NASA and be very, very informal in terms of discussing how I see things going and so on. And if you need to have copies more than what I have here, I'll be glad to take your business card and definitely give you a copy. One point I like to make, the views that I will express are not necessarily that of NASA. You will find that in my paper I definitely made this point, because there's a lot of stuff that I was reviewing as I was going through. In fact, as I changed the title of the paper, the first thing that struck me was the enormity of terms being used for technology. We had a visit by President Reagan a long time back at Johnson Space Center, and I realized that he mentioned the word technology at least 4 or 5 times. So you can imagine, nationally and internationally, how people use this term. I'll try to focus on that a little bit here in the presentation, but I have a discussion, a section on it in the paper itself. It turns out that advanced technologies and critical technologies are not the same, as you can tell. And there is in the paper a mention to this effect, but I'll also focus it in one of the charts. I'll also appreciate, once in a while, if you have a pressing question, you can stop me in the middle, because it looks like we'll have about 40 minutes for this presentation, as we don't have 3 papers. Let me then begin and show you this chart. We are famous in NASA for making complicated charts. As you can see, there's so much information on this. There's information on the left, on the right, and there's information vertically flowing from top to bottom. But it has come historically. We didn't make this chart in a day. It's ironically, it has taken about 25 years, 2.5 decades, to realize the insertion of technology and the dimension of technology, how you talk about it, how you communicate between scientists and engineers, for example, what technology means. As you can see on the right side, we have very simple. The program offices think of technology in 2 dimensions. Technology is either a R&D, research and technology, in which case somebody does that, or it's focused technology, in which case the program office, such as Space Shuttle or Space Station Freedom Program Office, will take this technology and qualify it for that particular program. So all of a sudden, only 2 dimensions. But you can see the interesting thing that people like myself have to probe and spend years and years trying to understand is this overlapping region. See, you have the basic principles. You can call that practically writing the theory of superconductivity, that's your basic principle, then you need to go into technology concept. And what kind of going to translate this basic principle into a concept? Do some analytical work, some experiment work in the lab, and then you begin to develop components and perhaps a breadboard. It's not necessary that you do all these steps rigorously, but finally, which I will focus a little more in my presentation, is this level 6 and 7, which means that even if a technology works here on Earth superbly, it may be useless in space. And therefore, a lot of our effort goes in terms of qualifying these technologies such that they give us the product that we are after in space. On the other side, then come the researchers who have developed this technology. They look at it at least in 4 different steps. The basic research, feasibility research, translating that basic equations into a feasibility proposition. Then, of course, begins the technology development where you start fabricating this high temperature superconductivity material. And finally, the validation. It has to go in a certain system, certain place, to a certain function, and therefore that kind of dimensionality. Now you can see how difficult it is for people like myself and others who pursue the path of technology within the agency to communicate these levels, because funding levels and other considerations are tied with this. Program schedules and other things are also tied. So it becomes a very multi-dimensional entity that you must pay attention to. Well, on top of this is then the terminology that you see in the newspapers. Very tough terminology, and in many cases very fuzzy. You will have to use your own intuition to quantify things. They're so qualitative, such as revolution. Gosh, this is revolutionary technology. From my standpoint, I drew this graph, but there is a book on this kind of thing. I don't have that name of the book, but it's referenced in the paper. The revolutionary means you have a quantum jump in performance. All of a sudden you go from a vacuum tube to a solid state transistor, and perhaps to a superconducting electronics, which will take very little power and very little space. The emerging technologies are supposed to be technologies that don't have that kind of snuff up performance right now, but in due course of time, they're going to take you a higher step than what we call the evolutionary technologies, where you're going step by step trying to enhance the performance of a technology. The idea is that at each stage, whatever you choose, it turns out that you reach a plateau. So the only way you need to make jumps is like going from a horse cart perhaps to a car, and from car to a plane, and then to a shuttle, and so on and so forth. And this will continue, whether we're here or not. The human race will continue that kind of quantum jumps in terms of what will happen in the future. So in the paper, as I said, after spending a couple of months on this topic, I even tried to diagrammatically show this multidimensionality of technology. I'm pretty sure I was not successful, but I was thinking of a sphere on which, first I thought I would draw a multi-dimensional space to show you that if you chose a technology, it will have so many attributes to it that you will have to quantify. Well, I failed. It's like X being a function of so many things. But in any case, if I could capture this thought in a figure, it would be something like this. There would be a zone of evolutionary technology, a zone of revolutionary technologies, innovative technologies, environment, unique technologies, which is very critical to NASA, because our environment is very special environment. You must pay attention to it. Program driven, you have space station freedom, you will definitely make certain compromises in terms of gearing of the technology towards that program. Then don't underestimate the fact that time and resources play a critical part in terms of what you choose and how you quantify and qualify the technology. This is something like that. And then there is the discipline unique technology, which means if it is propulsion, it's a propulsion type technology. If it is communications technology, it's a different type of technology. So you can imagine the axes kept getting bigger and bigger and bigger in terms of both the numbers and also larger in terms of how many axes were needed. So, in any case, just to give you an idea, then there's another thing. If you go to another way of looking at it, it's just things begin to get a little simpler and probably a little easier to handle. That is, you look at a lot of applications, A1 through AN. You look at applications of technology, such as a transistor. How many places you will use it? It turns out that you can use it numerous places. It turns out that if you then track back the discipline in which the transistor was used, such as communication, that becomes a few of them. Communication, propulsion, at least related to the space that we are talking today. So you have X number of programs, but you have a large number of applications of that technology. Then you keep going down, you find that if we had a revolutionary technology such as superconducting, high temperature superconducting diode, we would have a whole bunch of applications and probably give up this gallium arsenide and silicon technology altogether. So each of the technologies then becomes the root from which stem so many types of programs that utilize that, and then each program can use it in X number of applications. So in both ways, either you go from top down or bottom up, you'll find that this is not a simple term. That's why I'll not name him here, but the director of engineering once in a presentation looked at me and said, Kumar, what is technology? It's very, very complicated to define these terms and to have a grasp of it. Now, let me shift gears here slightly, because I am going to make this presentation into a certain focused discussion that you and I can make at the end of this presentation. I want to talk about education. This is a chart that came from Office of Technology Assessment. As you can see, they took the number of students that entered our elementary schools in 1967 and then traced back what would be our outcome of the number of PhDs, for example, a master's degree people. This is in natural sciences, mathematics, and engineering. It turns out, if I read this chart correctly, only 6.2% of the incoming students will have a bachelor's, master's, and a PhD degree. Particularly, the part that bothers me most is that only approximately about 1.2 or so percent will have a master's and PhD degree. That's not a good, healthy thing for a leading nation on this earth in science and technology. I think we should have much more population of highly degreed people. So what has this got to do with technology? Well, I'll tell you what it got to do with technology in my day. And again, a personal observation. Now, NASA can be defined in a multi-dimensional way in many, many attributes and many, many ways. For me, it's something like this. When I finished my bachelor's degree, I was just camping outside. I looked up and I realized that I didn't know anything about space. All I could see these stars. And anybody I have ever since asked questions relating to space, they have never satisfied. In fact, I recently attended an astroparticle physics school, and we had internationally renowned people. Some of the attributes of space, it's very difficult to even quantify today. So a space agency to me is something, a planner and executor, and on a national level of providing that space knowledge. We want to know what's happening out there, how many planets are there, how many systems are there, what's the extent of space, what's attributes and so on and so forth. We have an organization called NASA. That's chartered to do that. They're supposed to filter this knowledge. And especially, all we know at this time is that Earth is the only place where we have humans. Why? Why not some other place? These are some of the things that I think NASA has to do, and we have barely scratched. It's like we have not taken step one. NASA, on the other hand, offers very unique opportunities for people to do the things that they need to do in order to answer these questions. NASA is not necessarily answering itself all these questions. They are executing, planning, and perhaps facilitating the answer to these questions. The kind of things that we have, I think, are very unique is, first of all, space environment. Secondly, the facilities of people. And lastly, the identification of research ideas. To me, when you're doing a master's and PhD, if you look back to the Apollo era, you'll find that a lot of PhDs and masters were capably handling a lot of different developments in technology and science in industry, teaching in universities, have come from space-related research and technology. So we, as I see it, are the fertile ground of problems. Problems that can be worked for MS thesis, PhD dissertations, and so on and so forth. So I look at it as a partnership with academic and research communities for the greater goal of understanding what is out there so that we can benefit here on Earth. So that's educational aspect of space. Let me now focus on something else. While I was trying to do this paper, I also realized I kept writing 3-4 times, we need to qualify this for the space environment. And I realized, what's space environment? How am I going to communicate here? What is space environment? Again, just like in the case of technology, I found myself grabbing hold of a question that I didn't have an answer. It's a multi-dimensional entity that in some ways you could say there's electricity there, some places there's gravity, there's debris, there's magnetism, there's atmospheres of different kinds, gravity of different kinds, 1/6 of the moon and so on and so forth. Electromagnetic radiation, that itself is a big thing. Then there's a thing called void. Void is nothing. And NASA has, as yet to grapple questions like that. What's nothing? We have to sense that. We have to tell people what's nothing. Seismic information, particles, space. Space to me is length. For example, if you are conducting an experiment that requires 3 million miles, I may not be able to give you here on Earth. We are populating the Earth so densely now, quickly, that some of the experiments, some of the far-reaching things may have to be done in space. We have to use space perhaps as a laboratory. Then there is the time scale, the infinite time scale. Acoustical and temperature, big thing in space, as you know. So there are so many attributes, and when you talk about technology, you must take into account where is this technology going to work? Is it going to work efficiently, and so on and so forth. Well, again, let me focus on one item there, and I want to make one point. I don't know how well I can make it, but since this is so informal presentation, I'll try my best to make it. Look at the electromagnetic spectrum. What this spectrum lacks is 2 other dimensions, and I have given enough dimensions here, so I quit. I just will consider only one dimension. That is the frequency aspect of electromagnetic radiation. It starts with 0 DC, and it keeps on going higher and higher and higher. There's no limit to what kind of particles will be out there, and what kind of energy they will have, and what kind of frequency they will exuberate. Now, at least there are 2 dimensions that should have been here on the chart. First, there's an amplitude associated with these oscillations. I didn't want to bore you with that. Second, there's a spatial distribution. Some places there's one kind of radiation, other places there is another kind of radiation. I didn't know how to put that information on the chart. You can see how things get kind of a little complicated. But in any case, what is the point I was trying to make is this. If you look to this spectrum, and you notice that your eyes are capable of only a fraction of sensing this spectrum. So if you would depend on characterizing the radiation environment with your eyes, you would fail miserably. Because the only place you could sense perhaps is in the optical if your eyes were perfect. And that also it will graduate. There is a certain limit that it would reach and it would quit, below which it would not sense in terms of amplitude. So what did we do over the years, past 300 years or 3,000 years? We try to develop technology to sense, to bring back home. If I have a high school student, I can tell him what is a radio wave. I have an oscilloscope, I can bring it, focus it, I can tell him what the frequency is, and so on and so forth. So we have developed technology to reach the parts of the spectrum where our capabilities quit. Now comes the punchline. And again, a little bit controversial. I feel like when you go to the extent of trying to quantify space, I'm not too sure if we are mentally capable or will ever be mentally capable to comprehend all the phenomena that have happened in space. The Big Bang Bang theory says, there was this Big Bang and then comes 10 to the 43 years ago, something like that. The point is, what was before then, 10 to the 100 years ago? What was there? There's no limit to time. So things kind of get tough. Well, one way, humble way, I see is what NASA does. You begin to develop technology, you begin to develop the infrastructure, you begin to go out there, reach into the space. Pretty soon, maybe after 100 years or something like that, we'll have a better picture of what the universe is all about. We have already made strides in the last 25 years. We have revolutionized the way we look at space. That's my bottom line. So it's a question of trying to do something impossible that we cannot do as human beings, or trying to complement and supplement our capability with infrastructures, technology, vision, whatever sensors we need out there in space, and definitely human interaction to bring back to us what is space. So that's just a little thought process there. Now, I'll shift here slide. Next few charts, and I'll quickly go through next few charts because they are not significant from another dimension. But what they are is, it's not so simple. Given X number of dollars, X number of human hours to work on a certain technology, it has become obvious in the last 2 decades that you must spend a whole lot of time deciding what is to be done, when is it to be done, and why is it to be done, what should come first. So it turns out that this is an elaborate process. One that in the beginning, when I joined NASA like in 60s, we were, just sitting, huddling together, yeah, this is important, let's do this, because it will be needed in such and such place in the sky. That kind of thing. But over the years now, things have matured to the point that now it has become a discipline itself. How do you develop a strategic plan for the whole agency, for example, for a center, for a program? How do you quantify and qualify requirements? What constitutes a requirement? And then this process keeps on going. But the important thing is that technology planning is just like the first story of this building. If you didn't do it right, the whole building can collapse. And there are so many shades and attributes to that planning, and I'll show you a couple of examples of how we do it in NASA. But the important thing is that managing and planning, they have to be in a loop. It's a process. It's a process. And sometimes, which I'm not too sure if we're ready to accept, there are failures in this process. And part of it is that we have to agree and accept that, because this is research and development. It's something that we have some feeling that if we did this particular technology, it would get us this from this point to this point. It would save us 1 watt of power per minute if we switched from this technology to this technology. Now the motivating factor is, if you save 1 watt of power per minute, you multiply it by 60, that's 60 watts per hour, multiply it by 24 hours, multiply it by 365 days, then multiply it by 20 or 30 years, you are on the moon. Pretty soon you begin to realize that you may have something revolutionary. Although it's teeny tiny, but once we are in space, and we are using space just like a laboratory, our own extension of San Antonio, then we realize that we must pay attention to these efficiencies and to the technologies that will get us there. So anyway, there's a process that leads us. Let me give you an example. In the Space Station Freedom, which we have struggled for the past almost a decade now, and all the technologies that are needed are in there. Now, we're also working on extensions of technologies, for example, what we call the Globe Space Station, or extension of the space station. And it turns out the process is, you look at the evolutionary requirements, you look at what's going on in technology world today, and then finally, you look at what you need in terms of technology drivers and in terms of detailed technology needs and requirements. That then becomes a focused technology program for a program such as Space Station Freedom. We have similar requirements for Space Shuttle, but I just want to tell you that it's a process, it's a flow of events that takes place, and the thing that is most difficult at the end is that you always find the resources are so small and the amount of work that you have to do is so large that it's almost, you begin to pull your hair because you have to decide between two technologies, and unless your process and your priorities are set right, it's very hard then to say, we must do this first. And I think we have done a real good job in NASA of learning about these processes. I wouldn't say we are perfect. One of the processes, I'm giving you an example, is this process. That was the Space Station Freedom. But we have other programs such as the shuttle, and then there are other advanced launch programs and things like that. We were looking, our headquarters issued, we call it Code M, Office of Space Flight, a call from different centers. What do you think the technology needs will be in these programs? It turned out that there were 800 serious items viewed by centers. As you know, a center submission goes to the director of the center, and therefore it must be very serious. It gets scrutinized many, many times. Can you imagine 800 technology items? Turned out, and part of the reason why I wanted to show you the chart is, then we handed down, then the team evaluation took place, they only crystallized into about 22 categories. For example, many of these items that have come from different centers belong to communication technology. Many of them belong to tracking technology. Things of that sort, propulsion technology, power technology, what we call closed loop life support system, things of that nature. Boiled down to only about 22 disciplines. And it turns out that from those kind of then categories, you narrowed it down to 2 or 3 in these particular disciplines. That means from approximately 800, you go down to 60 or so technologies that come out at the end. Now, here's one reason why I want to show you this chart. The process of first gathering that 800 requirements and then nailing down the top requirements to 60, that's not an easy thing. And I'll tell you in a minute what enables that. But before I do that, let me show you a couple others, and I will not dwell on them. This is another process that our avionics working group, we have a major avionics working group for the whole agency. It involves industry, involves universities, and so on. They have taken all the way from step 0, looked at the whole space and air program, try to understand what the needs of avionics technology are, try to make it an iterative program so that you can understand the performance, the economies, the processes, and finally come up with an integrated operations list of technologies that need to be done. And you can see, because they are avionics, they put a plus-minus feedback system that allows them to adjust priorities and allows them to adjust the resources. And continuing on the same trend, if you look at another aspect, that's the avionics working group. This is the sensor working group, one of the earliest working groups that I have been a member for almost 15 years. It's incredible how many steps we go through to decide what sensor technology we need. Turns out that there's so much iterativeness and so much, each of the categories, for example, if you take cryo coolers, we have to debate on what are the technology trends, where is this going in terms of next 10 years or 20 years, what resources should be dedicated, what is the industry doing about it, what's the whole world doing about it. So all those factors have to be really incorporated in the strategy. As you can see, it's a very elaborate roadmap that deals with that kind of flow. At Johnson Space Center, we developed a slightly modified process, as you can see here. First of all, we look at requirements from the major programs. What are the requirements? What do people tell us? The people who drive those programs. You look at technology opportunities. You need to know what the industry is doing, particularly each of our major industries in aerospace has an IR&D, internal research and development effort. That's a crucial effort. That's where the industry sits down and says, I got this teeny tiny amount of money, 1 or 2%. Where should I invest it? So we take an account of that. That's a critical thing for us to know what are the industries doing. We have a center director's discretionary fund, very little money, about 1.5 million. But it's crucial to us because that's where we put our very advanced ideas. People at working level come up and say, I have a bright idea for doing this particular technology or this particular item. So we look at all these opportunities that tell us the status of the overall technology, where does it stand. Then you have to have a technology criteria. The technology criteria is generally strategic planning. What are the priorities of the programs? You don't want to do a technology that's needed 10 years from now today, as opposed to what's needed tomorrow. So there are time factors, of course, resources, and all the sponsorships, which tell you about the resources. You mix all this together, and if you have the right coordination process, you will determine the right coordinated requirements, you will determine the right coordinated technology thrusts, and that's what this process allows us. And in the center, what we have done, we have made a technology coordinating committee, and then we have a technology steering committee. The technology coordinating committee looks in a very impartial way at all the disciplines and at all the priorities, and tries to then say, this is the priority list. And technology steering committee, which has even higher level authority, then determines which goes first and which doesn't. The steering committee is made up of the senior staff members, and the coordinating committee generally from managers of technology as well as from experts of technology. Now, I also don't want to leave out here examples from Air Force, Navy, and Army, but I have here Air Force and co-chairman of this Space Operations Subcommittee. Turns out it's a similar process there also. There's a chart from the Air Force, and they have to also start with unified and specified commands. What are the mission needs? What is the mission? And break it down with a work breakdown structure, see where the technology can be inserted, what kind of priority that technology must have. So it looks like the flow is similar. The flow is similar. My punchline will come in a few seconds. And here is another chart I'd like to show you, and that is that's another example of Air Force. You see where they take all these safety, human factor, security. It's that top-down process, that all the attributes that must be satisfied have to be accounted for, and that's what determines the technology trust. Okay, I think I'm getting a little bit behind, but I'll catch up. I'll skip a few talks. I wanted to give you a little scenario of technology requirements as far as NASA is concerned. NASA sees, if you look at the Augustine report, that's where this chart I built from. Some people say you can build a lot of charts from Augustine report. I tell you, I only built 2. This one and the next one. But it does tell you, if you look to the 2 prime things, which is mission to Earth and mission from planet Earth, it tells you then the infrastructure that you need. Once you have the infrastructure and you have the capability that you need, you then begin to find out that those are your drivers. You need, for example, transportation and associated infrastructure. I'm not going to go through the problem. By the way, this is all given in the paper. Space station freedom. You need the infrastructures that allow you, stations that allow you to do the things that they allow you to do. Quantify the type of technology that you need. So then you have the science and technology programs and missions. You're there for some reason. That's your reason. And you have to be there for that reason. To be there, you have to have stations. You have to have planets, such as moon. You have to sit there and gather this information. Then what kind of information? You have a whole bunch of missions that relate to that. Life sciences, space physics, astrophysics. I talked about it a little bit. Of course, the space exploration initiative that most of you know very well. And then there are a couple of other attributes that don't necessarily come jumping at you just like space shuttle and space station freedom and other programs come. And those have to do with improvement of operational systems. One of the things that I think will happen in future, there will be a lot of attention to how to make things efficient. We have paid a lot of attention to how to get there. That's a big thing. If you look to the history of space, it's not an easy job to get there. So you have to do something to get there. Now is the chance for us to look at programs like shuttle and say, can I save $1 here? Can I save 1 hour here? And so on and so forth. And that it will come. Whether it's going to come regardless of it. Because efficiency, when you repeat a process, efficiency will just jump at you. And that's the reason why I wanted to make that point. Because a lot of technologies that we have out there today could be matured and could be used for getting that efficient and safe mission going. Then there is enabling technologies to incorporate requirement changes. None of the programs that I know of that NASA has done have been operational. You know, it's not an operational agency. It's not like, okay, we did the Earth resources, for example, we did the Nimbus satellites, somebody took it over, NOAA took it over. Hopefully, United States Department of Agriculture will do some of the things with that, and so on and so forth. But as far as I'm concerned, the biggest technology demonstration in this century has been the Apollo. The item that we have to demonstrate is take a person, a human being, and land him on the moon and bring him back safely. Now you can divide that into elements and sub-elements and anything, but that itself is a demonstration. Because next you have to do the same thing for Mars and so many other planets. So you have just, in my opinion, covered the step one. So it turns out that we will be looking to issues that allow us to do things not as one time, perhaps, but as was mentioned this morning, as a space carrying nation, repeat this process and go farther and farther and gather more and more information. Here comes my chance to sort of skip quite a few slides. But first I'll show this. If you look to where we have been and the number of, for example, days that we have been in space, by the way, as you and I know, our Russians on this Earth have done much better in terms of keeping the records, the number of days that they have been in space. But, so in any case, our hopes are now for the space station, to kind of like go much further than what we have done in the space Skylab arena. But it turns out when we go to the lunar outpost and we go to the consolidation phase and then we go to the Mars missions, we're looking at extended duration of human presence in space. And that itself is a major driver for a lot of technologies. Just being there up there for a few hours is one thing, a few days is one thing, maybe a few months is one thing, but having to do this sort of thing for years and years to come and having to have a permanent presence on the moon, which would be beautiful. I think everybody will love once that gets so routine. Maybe my great-grandchildren will be enjoying that privilege of going to the moon and coming back. But it's this is the kind of thing that we need to work with. We need to work with a situation where we are not going backwards, but we are going forwards. We need to extend the duration, periods of duration in space. Okay, here's where I can skip whole bunch of thoughts. That is, if you look at the space exploration initiative which we have done in the last 2 years and decide what type of technologies that you need, it's incredible how many space which are not 30 or 40 years old, but which are 30 or 40 years new in terms of what their scope is, so that they can be translated into products here on Earth. Now I have a chart in the table. You will find I have discussed these elaborately, and NASA headquarters has a working group to look at each of these disciplines. Example is here. You look at space transportation and it quantifies and qualifies, and not necessarily exhaustively. At least it gives you a version of what is needed as we see it today. How we see it next year or year after may be different. Okay, I'll skip most of these charts and go into another example. If you take another example, we have the space transportation avionics technology. I told you earlier, we have a space transportation avionics working group. Dr. Ken Cox from our center heads that. It's a multi-center headquarters industry group. And they have identified their technology needs. Avionics is a big thing, and it's such an enabling thing, particularly when you think of revolutionary things that we have to do in space in terms of lunar outpost and Mars missions. There will be a lot of docking and rendezvous and a lot of operations that have to deal with avionics. Now, again, skip. Another aspect is what I call space operations, applications, and research. I have to show you this because we're going to hold this 5th time, the workshop at Johnson Space Center, July 9th. This is not an advertisement, believe me. but I just wanted to tell you that we'll be meeting 5 times. It's a joint group of people, Air Force and NASA people. And we look at you can say agency cooperative efforts. We're trying to minimize, overlap of things, maximize using each other's technology and methodology as well as what the products are. But I'm involved in the operations world, and you can see there are several things we have identified in intelligence systems, automation, life support. Human factors is a big thing, particularly if we have to go for these long duration factors and environment we have to understand very well. Space is getting now crowded with a lot of things. Among others, it's also debris that we must concern. If you see my chart on space environment, I mentioned specifically debris. And as the number of nations that become spacefaring increases, which you and I know there's going to be a whole lot of nations that like to do space, then that kind of concern you have to do. You have to find out what the environmental interactions are, and a lot of technology is going to be needed in that direction. In the paper, you will find again a whole bunch of technologies identified for each of these disciplines. And I will skip this. We even took a look at one of the things that probably is going to revolutionize in some of the things that we do for space programming. That is the information processing systems. The reason why I say that is a lot of the knowledge that we have when we leave an agency like NASA lives with us. Believe me, it's very crucial that we pay attention to the fact that we must have a methodology to capture the knowledge of people. There's so many people out there who are highly knowledge, and sometimes this, because of the physical disabilities and because of the process of that we go through, humans go through, it's better to tap their knowledge and thoughts and ideas at an early stage. And that then becomes your rich library of things that ideas and technology and research that will come from. But that's one dimension of looking at space, is to develop these knowledge-based expert systems that will allow the humans to extend the reach, such as our eyes cannot see the electromagnetic spectrum in the radio part of the spectrum. Similarly, there are certain types of knowledge that we may not be able to comprehend. But if we develop the systems to comprehend those types of knowledge, to represent them, to capture them, I think it would be great. Particularly in the arena of where we're very, very strong at Johnson Space Center is the Mission Control Center. As you know, we control mission. And there are a lot of important people who left in the last decade or so that we should have tapped their knowledge. So we must pay a lot of attention to this, because as we go in space, a lot of things may have to be done autonomously. And you would like to use humans for the higher level things, not the lower level things of mundane, repeated type of operations and processing of that. Okay, I'm coming toward the end, and we even took a look at some of the critical technologies that we need for space. Are they important to the private sector? We have a group called NASA Science and Technology Council. It has 2 members from each center, and it has 2 members from NASA headquarters. And we grappled with this for about 6 months or even more. Try to understand what are the critical technologies, the high-tech technologies that would have a significant impact and payoff in terms of the private commercial sector. We came up with such things as adaptive automation, information acquisition and processing, etc., which I showed you earlier. There was about 9 areas that we identified. Transportation, of course, aeronautics has been such a significant contributor to our airline industry. That it's incredible what kind of payoff has come from that. Materials, a lot of things that I see now in spin-offs for the last decade come from the materials that we have developed for space environment. Here's the last chart on that, where I didn't go into my point line. The last chart, optical communications and photonics. Why is very high frequencies? A lot of times some people call me Mr. High Frequency. Since this is high informal, I'll tell you why. Because I keep on saying we must go higher and higher in frequency. One of the things is that your antennas get very small. How would you like to have 3-foot dishes on the moon, 15 or 20 of them? It's unmanageable. On the other hand, you can make these at 100 or 200 gigahertz, something like a town. The other thing is on these big antennas which are used for low frequencies, the information that you can put on because of the frequency, carrier frequency being low, is very low. So you want to go higher in frequency to get more and more information. I could spend a whole bunch of time with you, but let me also make one point. The higher you go in frequency also, the size gets very small. Also the directivity can get very fine, so that if you have a laser between 2 points, you haven't lost a thing. You have sent some energy here. If you capture all here, it hasn't gone in space, such as the radio station here in San Antonio. So there's a lot of attributes such as this that really push us in higher technology. It's not that we're crazy, but it's for getting technology for the sake of technology. But it's just because it has such a payoff in space. Then there is the nanotechnology, which I don't have time to explain. I think there's a workshop on nanotechnology. And energy generation and storage is another thing. Now, the last 2 shots, and I am done. This is the bottom. You look to the national scenario, you'll find out that the attrition that I was talking earlier about education, it turns out that we need more than 600,000 mathematicians, scientists, and engineers by the end of the century. More than what we are planning to do right now, 600,000. Out of which, if I'm not mistaken, 275,000 engineers are needed, according to US News and World Report. The latest issue says 275,000 will be short by 99 if we don't act now. So education is an important aspect. Now, it turns out that all those charts, 5 or 4 I showed you, and I could have showed you another dozen, where we iterate this process and try to understand what we need to do next, what kind of program, what kind of technology, what kind of research. It comes from humans like us. We're the ones that develop the plans, execute them, and make them happen, right? So, therefore, the crucial commodity here is expertise. Crucial commodity here is education. The nation that has the expertise and education is going to be the space-faring nation. Right? So I sat down and thought about it for a couple of days. I gave you this view graph. It says that all this strategy, all the plans, all the technologies that we develop, they feed back. They eventually feed back to our education system. Certainly at the higher degrees, there's one-to-one. I've been working with a lot of doctorate candidates myself, and I've been working with postdoctorate fellows. It's a one-to-one correspondence. They love to work on these things, and there's a payoff in the industry, which is another job. And then expertise. How do you gain expertise? You have this infrastructure of laboratories. You have these problems to work on. You have these technology lists to work on. If Kumar says we need nanotechnology, it's going to happen. If we identify critically that is needed, and therefore people in the United States, higher educated people and those who seek expertise in that nanotechnology will work on it. And pretty soon we have projects. Projects will be managed. So it's an iterative process. You develop the education system, you develop the expertise, pretty soon you have the ingredients needed to make this #1 nation in space. One more job. That's this. If you look at spin-offs, now I've been spending a lot of time on spin-offs. Personally, I was in charge of a project where we took the Apollo technology and built a system for heating the tumors. And this was a requirement from Stellan Foundation, and it worked beautifully. The system worked beautifully, and all the technology I took was from Apollo program. Turns out that if you look at our R&D, what we have done in the last 2.5 decades or so, there are 30,000 identified spin-offs where NASA technology has been of some use, someplace, somewhere. Now, somebody got bold enough at headquarters and gave a contract to Chapman Research Group. That's from Colorado. And they said, okay, let's quantify. Let's quantify. Quantify what? They took from 1978 to 86, the books that we publish, we call them spin-offs. And they said, okay, these were the list of technologies that were listed in that spin-off. They found that 441 of those, from those years, had directly been used by the U.S. industry. Then even that got out of their hand, to trace what the product was and what the revenue was from there. It turns out that they did track 259 cases and $22 billion of technology accrued from that, and about $350,000. So there's some tangible things. We're not able to quantify in NASA these kind of things. It's very hard to know where the technology is being used, and most often it's very proprietary. Because people are not going to tell you, I used your material that you developed for the space shuttle, the type. They just want to keep the process and the technology, proprietary, because that's their thing. That's what they sell. So there's a lot of payoffs here. And I guess with that, I say that space is a thing that has so many dimensions for us. And we must work in space. We must try to understand what we are doing and what we need to do. Thank you for your patience. I'm sorry it was a little bit long.
Thank you. Similar time frames in presenting his talk today. We'll hold off on questions for now. I'm sure that you generated a number of questions for Dr. Krishen. If you could possibly hold those off and ask them in the session. The second paper today is by Dennis Stone, who also works at NASA's Johnson Space Center in Houston, where he is assistant engineer with the Assured Crew Return Vehicle Project Office, and he is going to follow a similar presentation format on the floor. And
thank you. Speaking of technology. Everybody here? Yeah. You can't see? Important thing is not to see me, to see the charts. Pleased to be here today. Like Kumar, I work in the New Initiatives Office of the Johnson Space Center. And I think the talk you just heard is very important because NASA's probably the most crucial role in the development of space is maturing those high-risk R&D projects, the technologies that both government and commercial projects can be based on. So that's a very important area. What I'm here to talk about is the Assured Crew Return Vehicle, which is one program we're doing. As you know, the ACRV, as we call it, is part of the space station program, and we see the role it plays. Also, as you look at the project from its own standpoint of what it does and how it does it and so on, there's another view you can also look at. We have, I think you'll find a lot of innovation has been used, and some of that I think is very important in the recent history of the manned space program. And since at least a few people who have recently raised the question of whether there's going to be a space station, I think the value of what I'm going to tell you also therefore lies in some of its applicability of the process that NASA has used on this small project to other future projects in spaceflight. So keep that in mind as we go through this. The topics I'm going to go over are the mission of the ACRV, the requirements, some of the design concepts, where are we right now in the project, and the relationship with some other studies that are going on, like the PLS, or Personnel Launch System, and finally try to draw some conclusions. We talk about the mission, and again, this is not a mission in the sense of a shuttle mission. or a single flight, but mission in this context is used as the fundamental purpose behind a new system. So we're going to talk about the mission of the ACRV system. When Challenger occurred in 1986, NASA began a very sweeping reassessment of safety across all programs. And one of those programs, of course, was Space Station. At the time, this was the status of the capabilities to support the crew in any kind of emergency in the Space Station program. And it's still true today. It's a triad, if you will. There's safe haven capability, a redundancy built in, ability to isolate a module and go to another place and have basic survival equipment. The ability of the space shuttle to a fair extent to stop what it's doing and mount an emergency mission, although that does take some time. It can't be done instantaneously. And an onboard health maintenance facility that provides some degree of care as well as maintenance of the crew member's health. We certainly cannot do surgery in space, and there are some technology limitations in what can be done, as well as cost, volume, power, and all those other constraints. So that was the safety provisions for the space station crew at that time. But as part of those assessments after Challenger, we started looking at all possible scenarios that might cause risk to the space station crew. And this is, again, a typical NASA eye test chart. But the important thing, I think, is to note that there was at least an attempt to have a very thorough assessment and the identification of all things that could cause loss of life in low Earth orbit. The first was, in fact, the kind of thing that had just occurred, a stand down, as we call it, of the space shuttle fleet. And what that means would be another type of incident, for whatever reason, that makes it very unsafe to fly space shuttles. If this happened, of course, with a crew in space, their lives would be threatened. They would, of course, run out of supplies, and the medical effects of long periods in space and weightlessness would also present some very serious threats to the crew. Then there's another category called station emergencies. These include catastrophic failures and accidents, failures of subsystems. And on the next chart, I'll show you some externally caused threats. We tried to be honest, about this and understand the timing. In other words, if one of these scenarios occurred, how quickly would risk occur to the crew? Some of these are very non-critical. Many weeks to recover, and yet others, all we have are minutes. And so that turned out to be a very important driver in the selection of how we could assure the safety of the crew. And also, as we went through here, we tried to understand were there any occurrences in the history of spaceflight, either in our experience or that of the Soviets, that might suggest the probable occurrence of this sort of thing again. Because, in other words, has it happened once? And that's all this says. And it doesn't imply, of course, it will happen again. But I was surprised at the fact that so many of these did, in fact, have a real basis in spaceflight history. For example, of course, the Apollo 1 fire, explosion of Apollo 13, toxic spill that was on the Apollo-Soyuz test project on our side, and the Soviets had that as well. So you can kind of get a sense of the different causes of risk to the crew. Again, external threats, meteoroid hits, and what have you. And then finally, another type are the medical emergencies. These could be serious illnesses that occur, or I guess you could call occupational injury to the crew. And here, the doctors who were working with us were able to put some sense of a probability, very, very rough probability on the kind of occurrence they would expect on the space station. So with those scenarios in mind, the mission, actually 3 kinds of flavors of mission, were defined for the ACRV system. And they simply abate the 3 major kinds of risk-causing scenarios we just saw. They could return an ill or injured crew member when it's a life-threatening situation and there are no onboard capabilities to deal with that. Secondly, if the space station should become uninhabitable for any of those reasons you saw, all the crew members could safely return. And finally, during an extended interruption of shuttle launches, that the crew could also return in that scenario as well. Also, many people had suggested, well, if we're going to have this capsule, this capability to transport crew, well, NASA needs other things too. Some safety-related, others operationally. For example, bringing cargo down from the space station, bringing crews up on an ELV in the same capsule. Shouldn't there be some synergism, some return on the investment, and so on? And we had some good thoughts, and so we set out to see if we wanted to add any of these missions to the 3 mission. And there was a very, very in-depth study on all of these, looking at the design impacts, the cost, the operational impacts, and so on, keeping in mind the purpose for this, namely those 3 missions to show the safety of the crew. And all of them were, in fact, rejected after some very serious and objective scrutiny. The reason was that in a lives saved sense, they could not be justified. Some of them, even in the rescue sense, were extremely expensive, and they would really, if you will, corrupt perhaps the very ability of the ACRV to do these 3 missions. And yet, I think it has helped us understand both what the system is going to do and what it's not going to do. If questions come about, we can show cost data saying, well, NASA wants to do A, B, or C here. Here's what it will cost, and here's the schedule delays, and objective management decisions can be based on that. So we have a good sense of data of what goes even beyond what our system does to defend this mission. And with that approach, we have found a lot of support now for the ACRV. Virtually every committee that has studied it, and it seems like an endless stream of committees come along and take a look at what we're doing. It's been unanimous. They have all said, well, of course you need a way to assure the safety of the crew. The shuttle is not up there all the time. What are they going to do when it's not there? So it's had a very, very fundamental sense of a shared vision that this is necessary, and even as recently as the Augustine committee last year, late last year. So we think that we have a process, again, which could be used elsewhere to crisply and cleanly define a very bounded, well-scoped, well-thought-out mission for a system. I think that's very important in controlling cost. Once that was done, the next step was to write down some requirements, and I won't go through all our 200 or 300 requirements, but let me give you a sense of where they came from. The first step we found in writing even top-level requirements was to get a selection, if you will, of a way of meeting the missions. It turned out there are, at least initially, conceivably many different ways of meeting those missions. For example, a new ground or space-based emergency vehicle, a shuttle modified to have a much faster launch on need capability to stop what we're doing and get it off in a few days, that sort of thing. Either manned or an automated mission. Leaving an orbiter up at the station all the time. That was looked at very, very carefully. EOBs to bring more supplies. All of these things and many other options were looked at. And again, an agency-wide in-depth study. And it was concluded that a new, not necessarily high-tech, but at least a new design, space-based asset was really the only option that was anywhere affordable, and that also could do those 3 missions that have been so clearly settled on. Because a lot, particularly the requirement to abandon ship is one that really cannot be accommodated by any ground-launched asset. There's a need to do that in an emergency basis, and we're talking, as you saw earlier, 5 minutes, maybe less, maybe more. So that was decided that we need something new. Then the understanding of how will this thing be operated? What are the steps in the mission? So there's an operational concept. The emergency occurs, the crew gets in, they get away from the station, which is causing the risk to them, and so on. All the steps in the mission were defined in a preliminary sense. There are some major influences also in those requirements. The project manager said, this is going to be a lifeboat. Okay, a lifeboat, great. What does that mean? Well, it's going to have to be simple. Imagine a passenger ship. The passengers really can't spend a long time training how to run this lifeboat, particularly since they hopefully will never ever get in it. It has to be very simple. It has to be available. When the emergency occurs, you don't want to run over a lifeboat and find it's not there, it's down for maintenance. It has to have a high degree of availability. It has to be reliable. When you lower it in the water, you don't find it as a whole. It starts to sink. So it's got to work when you need it. And very, very important, it has to be affordable. A lifeboat, for example, shouldn't cost as much as the ship. If it did, you just wouldn't have any lifeboats. So those were major influences. There's an interesting standard in the federal government that the OMB issued called OMB Circular A109. And we really looked at this in depth. It's a very high-level document, but it talks about what the government's role is versus what the contractor and industry's role is. Because sometimes those get fuzzed up, and it causes some confusion. This provided some real clarity about exactly what we should be concerned with, and what industry should be let alone to do. The DoD, I felt, had a wealth of experience in developing requirements. They do it all the time. They have many, many projects. NASA in the manned spaceflight world has one every 5, 10, 15 years. So there's a lot of corporate memory, very applicable to this. And finally, the project, I felt fortunate because we had a clean sheet approach. We were allowed to try something maybe a little new for the Johnson Space Center in this area with the hopes of maybe saving some money and so on. So we were allowed to come up with a new process. And the essence of that was really that requirements would be stated in high-level functional terms. Often you hear about the big specifications, this thick, design it this way. We didn't tell them to design it this way. Our requirements are thin as in, if you will, at least in our project, because we kept it to functional terms. Transport 8 people from point A to point B. They were derived solely from the missions. There was no requirements creep, gold plating, different names we call it. A lot of programs. The book starts off this big, it gets bigger and bigger and bigger as the program goes on. We said, we want none of that. We're going to keep it thin. In fact, every now and then one gets thrown out, and we'll see if it works its way back in. And we also, and this goes back to the chart that Kumar had, where all the different inputs from safety and the environment it operates in, all those things are brought forward at the front end of the project to ensure that we thought of everything. The vehicle's going to have to be transported perhaps to C5A to even get to the launch site. we want to make sure that we understood exactly all the phases of operations so that we could write those requirements up front and not discover them downrange after some of the designs have already been made and go, oops, we forgot this and that. That's what costs money. It costs very nothing to write them in, very little to write them in at the front end of the program. And again, we used the DoD standards, I think, found was very applicable. And this whole approach, we feel, is going to lower program risk. The cost should not grow, and we feel very, very confident about having a stable set of requirements. And this is a tough concept for many to digest the first time. They come up to me and say, well, what's the cross range going to be? Oh, is it going to land in the land or the water? And I go, I don't know. Those are tradable. When we stated the functional requirements for this thing, we didn't say take people from 8 people from the space station to the surface of the ocean. It said bring them to a facility on the ground. So as far as the mission was concerned, this thing could have look like a helicopter and land on the roof. Now, of course, that's impractical, not cost effective, but the point is the requirements don't address specific design solutions on things that are so tradable. What this really enables are the contractors can then be innovative and truly look at a broad range of design solutions in order to pick the one that they think is the most cost-effective solution. Again, very unusual for the government. People are coming over and saying, okay, the right requirement, it shall be painted green. That's just hypothetical. But when we get those inputs, we say, good idea. Thank you for your input. Talk to the contractors. Give them your thoughts. Share your design input with them. They're the ones who are going to make those decisions, of course, with our oversight. So we are keeping all those things out of our top-level requirements. Let me talk about the design of the ACRV. Once the requirements were put in place, and they've been in place now for about a year or two, and we've been using this time to validate them, NASA also began doing some in-house work on different design solutions for the ACRV. This is just the vehicle, but there's the rest of the system we'll talk about too. But here's some. I'll spend just a moment talking about. The SCRAM is, I think, like typical NASA program, we invented the acronym and then tried to find some words that fit it. Seven crew, rescue, something like that. But anyway, this is a simple pressure shell, about as simple as they come. And it's mounted to a heat shield. And this concept, we used the heat shield from the Viking Mars link. Again, existing aerodynamic characteristics and so on. It was developed as a potentially very, very low-cost solution. You'll see a lot of existing shapes, because apparently the aerodynamic testing of new shapes is a very, very expensive process. The government used to recover film from orbiting spy satellites before we were able to beam them down. And the Discoverer was a shape developed many, many years ago for those re-entry capsules. This, of course, has been scaled up to the size of this concept that the crew in. But again, existing aerodynamics. Our old friend, the Apollo, again, scaled up, was looked at. And many of you have probably seen some pictures of the Soviet experimental space plane. Our government apparently was very interested to see those pictures as well. And so we've been looking at shapes of lifting bodies in that same class of performance to see what kind of benefit they may have, not only for this program, but for other applications as well. The operational approach and how you get them out of the vehicle to the final end of the mission include landing on the water, something that I know we've all seen before. We looked at land landing modes as well, and even particularly for the lifting bodies that can actually maneuver because of their cross range and get a precise point, when you look at runway landing capabilities. You'll see later those probably are going to be a bit more expensive than we can afford. But also in the operational concept, I want you to note the lack of the U.S. Navy in this picture, and the lack of a massive caravan of 20 or 30 vehicles and all the sniffers and people in those funny suits in this picture. It quickly became quite clear that it would be very unwise to have a standing army, if you will, of these kinds of ground-based assets, training and always in a state of readiness for something that you hope would never occur for 30 years, which is the planned lifetime of the space station. So we clearly had to, we were going to afford this, come up with some ways of rescuing the crew and getting them to where they need to go quickly without any major NASA investment. So we found that there's a worldwide network of search and rescue forces. When an airplane crashes in the middle of the ocean, when boaters have problems on the coast, there's an infrastructure that already exists to handle them. SARSAT is used to identify the location of people that have had problems like that, and rescue forces are dispatched. It's amazing. The military is involved, the Coast Guard is involved, civilians are involved, and it's true not only in the United States, but all major countries as well. So we think the operational approach will be to notify the neighborhood SAR force, have a few pre-selected landing sites, and to go away. We have two contractor teams working on the ACRV. One is led by Rockwell, one is led by Lockheed. Everything I've said here is NASA in-house, NASA in-house. Well, what are the contractors doing? Unfortunately, I cannot tell you because it's competition sensitive. I mentioned A109 earlier. What it says is the government should produce those clear functional requirements and then let your contractors go off and do a trade-off and allow them to compete. In the military, that's gone one step further. They design it and they actually build a sample. We have what they call our fly-offs. Well, NASA doesn't go into big production runs, unfortunately. So we are, though, having a design competition, and may the best contractor win. This is hypothetical, but I'd like to illustrate the point by asking you to imagine, if you will, the whole design space of all possible solutions to the ACRV system's requirements. Team A starts narrowing in on where they think the lowest cost solution lies. Team B starts doing the same. And the point is they could be different. One might have a water lander with a low cross range because there are many landing sites in his system. Where the other could say, well, I want to land on land just in the continental United States. Some need a little more cross range and so on. Add some more loiter time so your landing opportunity arises. The point is, this is the trade space. The contractors are allowed to diverge where it's prudent. And by the end of our parallel studies, there could be two different design concepts. One will then get chosen during the final procurement, and at that point, if one of them goes away, we'll know what the answer is. But the government is not synthesizing and taking information from one contractor and offering it to the other. That is very unique, at least at the Johnson Space Center and many other programs. But to do our job, we have to integrate this vehicle into the space station. There are a lot of technical issues. We have to get ready to operate it. We don't know which of them they're going to be. So we are developing a concept in-house, and these parameters chosen for this detailed design. We call it the reference for external integration. It simply allows us, while the contractors are doing their behind-the-curtain activities, we can continue to plan how the vehicle will fit into the NASA infrastructure with this as sort of a pathfinder. Also, there's a lot of testing that NASA is doing in-house, both on the in-house developed concepts as well as sometimes contractors come in and use our testing facilities. This example is a wind tunnel model of the lifting body shape that I discussed with you just a moment ago that we saw the Soviets were looking into. And at the Langley Research Center, they've done extensive work now on that and similar shapes and tried to fine-tune it. So that kind of work supports our program and others. Let me talk a little bit on the programmatic side, not in any great detail, but just sort of a sense of the schedule, where the project is right now. And this goes off the scale here. We started back in '86, so there's been a lot of work done. But where we are now is the requirements, as I mentioned, have been clearly defined and reviewed and reviewed and reviewed again. So we're very stable there. The contractors has begun to define system concepts to meet them, and then they will select and refine those concepts and do some detailed design and a period of testing of those concepts as part of this design competition. Again, we won't be flying them off here, but certain elements could be tested in support of the selection. And after selection, of course, the phase CD, the development phase of the program, and the requirement is to be there when the station first is permanently occupied. And that, in other words, when the shuttle leaves, but it leaves people behind. And that right now is scheduled for late in 1999. How much does the system cost? And you see some numbers here. Let me give you a sense of where we're coming from on that. This is a chart that this is in billions of development costs on the vertical and time along the bottom. These points are cost estimates of the system. And you've seen the wide spectrum of design solutions that are possible and the wide spectrum, therefore, of the costs that go along with them. For example, again, the chart might be hard to read, but the higher ones, for example, are those lifting bodies that have a lot more capability, more cross range, and so on, and pinpoint runways. And as we go down, we come up with some much more basic, holistic kind of systems and so on. All we can say right now is a range of costs. And we're, in his recent testimony, Edward Truly mentioned a general range. We have a number in for budget purposes. But until the phase B is completed out here somewhere and designs are selected, we really won't be able to know what the costs are. But as the contractors go through and come up with their point designs, we'll be able to put some points on the curve. And knowing how the government works, the lowest point will probably be selected the winner. Certainly cost is a major factor. The final subject I wanted to mention today is the relationship of the ACRV program to other studies NASA is undertaking. For some time now, NASA's been looking at other means to launch people into space. A lot of these started after Challenger as well. Recently, under the title of PLS, or Personnel Launch System, we've been looking at things like that. And the Augustine Committee gave that whole study a shot in the arm last winter when they came out and said that there really needs to be at least provisions to, not now, at a future date, quickly develop a two-way capability. Because they were worried about the space station going unmanned if the shuttle, for any reason, should be unavailable to keep that logistic supply train going. And they said, well, in the event of a stand down, let's at least be able to get some people up and down to keep that international research facility going. So they supported that. And we're continuing to meet that objective, in studying ways, I should say, meet that objective. PLS is one possible solution. There are certainly others. And within the PLS category, modifying an ACRV to be a PLS is one possibility. It continues to be studied, and there are no conclusions right now, but the fact that we had done those alternate mission studies I showed you a while ago at a previous date, we know that the ACRV, basically a lifeboat, an ambulance, emergency departure, down-only vehicle, has requirements that are very distinct from a routine operational system that has to be launchable on an ELV and so on. Clearly, adding a manned ELV launch requirement to the ACRV would compromise the ACRV's major goals of being simple, reliable, available, affordable, and so on. Plus, the fact that unless there was a tremendous crash program, we couldn't do it in time for the space station's need. So there's some real concerns about that. Yet, on the other hand, we're not closing our eyes to the fact that NASA may at some point, somebody may at some point, develop a PLS. So when design decisions are going to be made, we are trying to darndest to be a bit more enlightened about them and to not do anything that would preclude either the actual ACRV itself or at least the design of the ACRV to be used as a starting point for other programs like PLS. So for nothing more than saving some money and getting some more out of the investment. I did bring along one chart of the kinds of things that are being looked at for PLS. This is out of our engineering directorate at JSC. And this is interesting. I'm not prepared to talk a great length about it because I'm not working on the PLS, but the capsules, some of which you saw in some of the other photographs, biconic shapes, lifting body shapes, including the one you saw earlier, and even more complex designs like lighter class. I think the key message here is that the ACRV, its window is off on this extreme left side of the spectrum. Another technology probably can. But the synergism of those two programs is real, and we certainly want to both make the most of it. So let me try to conclude with a few thoughts. I think ACRV, we've convinced ourselves, is unique in recent manned spaceflight history. It has a very discrete and bounded mission. A lot of programs have been infrastructure building, in the sense that they have to launch as much as they can to low Earth orbit, accommodate as many uses of the low Earth orbit environment, or either because we're lucky or whatever, we're not in that category. The ACRV has a certain number of people delivered from point A to point B. Not 3.5 people or 4.5 people, but exactly 4 warm human bodies. And so the mission is very, very clear. The requirements, the approach that is used are high level, yet they're complete. Again, they're very thin, and a lot of people in our environment say, well, gee, when are they going to grow? This is not. And we're very proud of that. Design innovation has been enabled, and again, this will allow cost to be saved, better way to do the job, and risk to the project will be lowered, and hopefully that'll eventually save lives in space. So hopefully I've given you a little interesting flavor of what the ACRV is like, and perhaps also a sense of the process we've used, because we really believe that the innovative process is going to be applicable to other new ventures in the field of spaceflight. And if there is any time, I would be happy to entertain any questions too.
Is there any discussion with the Europeans today on the potential of using Hermes or something that is in development as in a cooperative scheme with that agency?
I guess if we're going to proceed with the space station, it's clear from all these committees I showed you that we have to have some kind of capability there at the very first moment the space station is manned, when that orbiter leaves for the first time. We have looked at Hermes, and we've talked to them a lot. There's no really clear sense, though, that that system will be there when that need occurs. If there was, and if there was a sense that it could do the job, perform the missions, and do so affordably, it's cheaper than these small lifeboat kind of systems. I can't imagine, it certainly can't rule out the possibility of pursuing that. So the real concern, though, is it going to be there when the station needs it?
Well, again, you wouldn't want the Hermes people to design that in such a way that if you did want to use it as an advanced single person or whatever, keep people up on an expendable launch vehicle, that when it got there, it could dock with it, you know. You would hope that somebody had the sense to design it in such a way that it would not be incompatible with what you have.
As far as I know, although there have been attempts to do this, and I don't know why they haven't proceeded faster, but, and you probably know too, there are no international standards right now for much of anything in space flight. The whole idea of rescue and dealing with emergencies has been the strongest driver to get the international space community to come together to start developing those kinds of standards. But I think there have been some conferences, and I don't know much about it other than no standards have been issued yet. And so when the two programs have to integrate, they choose a hatch size, and they develop those interfaces optimized for themselves. And really, as a result, at this point, we see a family of very incompatible spacecraft, and nothing is changing it. Yes.
Yeah. Along that same line, was there any exploration of buying a couple of surplus Soyuz capsules and designing an adapter rig?
The Soyuz has been looked at. Some of the problems we saw immediately was, number one, its size. You can fit, we're not stretching the hardware, just taking them right off the factory line. They can only fit 3 people. And also, they don't have the on-orbit lifetime to sit there and wait for an emergency to occur. The benefit of developing a new system is you can design the materials and the systems to just be dormant, sitting there and be activatable in an emergency and work, and maybe not need maintenance for 5 or 10 years, this sort of thing. Whereas the Soyuz, explained to me, must be brought home in 90 days. And so that turned out to be, even with the lower cost, if you just multiply those numbers quickly, you're bringing them up and down so frequently they might not be feasible.
Maybe just one more.
And any for Kumar, too. He was here first.
I guess this is for Kumar. Is NASA looking at technologies related to, or I haven't seen NASA looking hard at technologies related to processes or some of the more softer engineering disciplines like supportability, safety and reliability, things that are not necessarily hardware oriented. Is that going to be changing with the SCI program as it will require more effort on those disciplines?
Yes. You brought up a very good point. If you look to the Office of Aeronautics and Exploration Technology, OAEP, that's our code R. To my knowledge, we didn't have a discipline called operations technology at the time. We had the propulsion, power, information systems, sensors. In the last 6 months, they have added a new category called space operations. That's where the survivability, reliability issues will be put in. So you will see fundamental technologies being now addressed in that.
Thank you.
thank you. I think it's high noon in San Antonio, and I wish to thank the speakers for some very interesting presentations. And I wish to thank you, the audience, for attendance and paying close attention. I hope you enjoy San Antonio while you're here.